there, it's Shannon Math Chick Myers, and today we are starting our differential equations course. I am basing this guided notebook off of the ZIL 11th edition text, and we'll go ahead and get started by looking at definitions and terminology. So at the end of the day, we want to be able to determine whether a differential equation is ordinary or partial, classify a differential equation by order, linearity, and verify a solution of a differential equation. So let's warm it up. It might have been a little bit since you've had your calculus class going on. So let's find the indefinite integrals of these bad boys here. If you'd like, you can pause the video, work it out yourself, and then check to see how you did. All right, let's check it out. Here, you can either use pattern recognition, seeing that the cosine function is the derivative of the sine function, or we can do an actual u substitution, changing the variables. If u is equal to sine at x, you could have done cosine at x as well, but then you would have needed to adjust by a factor of -1. Then our du is equal to cosine at x times dx. So we'll have, this will be equal to the integral of u du, and just in case you're wondering where it came from, the du is cosine at x times dx, and u was sine at x. And then just that simple power rule, we'll get 1/2 u squared plus our constant of integration, which is 1/2 the sine function squared at, and we're evaluating it at x, plus our constant of integration. So notice that with regular calculus stuff, like Calc 1 stuff, typically we didn't use a subscript in our constants of integration because of the fact that you typically, if anything, you were maybe adding or subtracting multiple constants and you still just called it plus c. But we'll be looking at constants in a more direct manner, heightened intensity in this class. So, all right, hopefully that one went okay. Let's go ahead and look at the integral of natural log at x dx. So here, hopefully you realized with a little bit of playing around that we need to use integration by parts. So if we let u equal to natural log at x, du will equal to dx over x. dv is just dx, and if I integrate both sides, we just get v is equal to x. So coming back over to the problem, recall that the integral of u dv, that's not a very good v, dv is equal to u times v minus the integral of v du. So we have the integral of natural log at x dx, that is equal to our u was natural log at x, and our v we found to be x. Sorry about the dogs. All right, so we're going to subtract from that the integral of v du. So that's x, and then times dx over x. So matching everything up, u was natural log at x, and du was dx over x. And then our v, we'll do that one in purple, our v was equal to x. All right, so the integral of natural log at x with respect to x is equal to x times natural log at x. I'll just write that prettier. Now notice here you can divide out the x's to be 1, and you're just integrating 1 with respect to x. So that will just be minus x plus c, and we are good to go. Just a little quick example of integration by parts. All right. First definition, differential equation. An equation containing the derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables is said to be a differential equation. And we shorten that by saying DE. So differential equations can be classified by type, order, and linearity. So let's look at classification by type. First of all, if a differential equation contains only ordinary derivatives of one or more unknown functions with respect to a single independent variable, it is said to be an ordinary differential equation. And of course, we've got a shortcut for that, so that would be ODE, ordinary differential equation. All right, so an equation involving partial derivatives. So you did some of those in Calculus 3, or will be doing some in Calculus 3. So if they contain partial or involve partial derivatives of one or more unknown functions of two or more independent variables, that will be called a partial differential equation. So we won't be dealing with those so much in this class. It is shortened by partial differential equation, so PDE. Now, notation. Leibniz notation is very useful because you know exactly what variable you're differentiating with respect to. So if you have, you're used to seeing this kind of like maybe dy, let's do dt, d squared y over t squared, dt squared, can't talk today. The third derivative would be d cubed y over dy cubed, dt cubed, etc. And you can go all the way to that nth derivative of y with respect to t. And here, with this one, it's nice because looking just at, I don't know, let's look at d squared y over dt squared. The y portion tells you that that's your dependent variable. And then the t right here is our independent variable. Now, prime notation, dy dt could be denoted as y prime. D squared y dt squared over dt squared, or with respect to t, that second derivative, could just be y double prime, y triple prime, etc., and all the way until, now remember, if you see parentheses when you are looking at the superscript in this context, then you would have that tells you it's a derivative. And actually, this one we didn't need parentheses around. I don't want to make it confusing. All right, now there's dot notation that's only used when you're differentiating with respect to time. So the way that it would look, again, using that same example, y dot would be the first derivative, y dot dot, y dot dot dot, etc. And then subscript is used quite a bit in partial differential equation classes, higher level classes. And so if you had you have your variable, and then y sub t would be that first derivative with respect to t, and then if you do y tt, you'd have that second derivative, etc. Okay, so we're going to see mostly the top two, these guys here. Now, classification by order, the order of a differential equation, and it doesn't matter if it's an ordinary differential equation or a partial differential equation, is the order of the highest derivative in the equation. So, first example, let's determine the order of these ordinary differential equations. So, here I've got, let me zoom it in a little bit. Now you got to be careful here because this one right here is third order. This one here is first order. So the whole equation ends up being, a third order ODE. When you're raising a first derivative to the fourth power, it doesn't mean that it's the fourth derivative. Cool? Similarly here, this one here is a second order. And then you've got a first order right here, another first order right there. So I would call this one a second order ODE. So those are kind Kind of tricky. All right, so next up, let's take a look at the differential form of a first order differential equation. Ordinary differential equation in differential form. Please assume that y is the dependent variable. All right, so we may want to put this in a different type of notation. So if we take a look at this guy, we could write it as dy dx in for the y prime plus y squared minus x squared is equal to x. Now, here, what we want to do is we want to put this in differential form. And so if we multiply both sides by dx, we're going to get 8y dy plus y squared minus x squared dx is equal to x dx. And then writing, prettying it up a bit, we could go ahead and we could say 8y dy plus y squared minus x squared minus x dx is equal to 0. Groovy? All right. So in symbols, we can express an nth order ordinary differential equation in one dependent variable by the general form capital F at x, y, y prime, all the way down to the nth derivative of y is equal to 0, where f is a real valued function of n plus 2 variables. For both practical and theoretical reasons, our text and we will make the assumption after this point that it is possible to solve an ODE in this form uniquely for the highest derivative, the nth derivative of y, in terms of the remaining n plus 1 variables. The differential equation, the nth derivative of y with respect to x is equal to f at x, y, y prime, all the way down to the n minus first derivative at y. Groovy? Okay, where f is a real valued continuous function, so this is the lower case, and is referred to as the normal form of capital F at x, y, y prime, all the way to the nth derivative of y equal to 0. So we will use the normal forms dy dx equal to f of x and y, and that second derivative equal to f of x, y, and y prime to represent general first and second order ordinary differential equations. So in example 3, let's check this guy out and write the ordinary differential equation in normal form. So normal form, what do we want to do? We want to find, beautiful, we want to find and isolate the highest order derivative. So do you see that this term here contains the highest order derivative? So if we isolate it, we would have 12x times the second derivative of y with respect to x is equal to 2y cubed minus 7y times dy dx. Now we'll go ahead and isolate that second derivative with respect to x, and that's going to equal to 2y cubed minus 7y dy dx, and then this will be multiplied by 1 over 12x. And I'll pretty this up a bit. This, of course, would be for non-zero x, non-zero x. And we'll just write this as y cubed over 6x minus 7y dy dx over 12x is equal to that second derivative of y with respect to x. Cool, cool? So that is normal form of an ordinary differential equation. Classification by linearity. Linearity. So an nth order differential equation is said to be linear if f, capital F, is linear in y prime all the way to that nth derivative of y. So if capital F at xy, y prime all the way to nth derivative of y equal to 0 can be written as, this will be kind of a long one, a sub n times x times the nth derivative of y plus a sub n minus 1 times x times the n minus first derivative of y. And you keep going on in that manner. Then we'll get to a sub 1 times x times y prime, that first derivative of y with respect to x, plus a 0 times x times y is equal to g of x, or equivalently, a sub n at x is equal to this is just, I'm not going to read it all over again. This is the equivalent expression in using a different notation, the Leibniz notation. If we can do so, then it is linear. Two special cases. Linear first order differential equation. Well, there's only one derivative, so it would be a1, a sub 1 times x times y prime plus a sub 0 times x times y is equal to g of x. And what do you think we'll have for the linear second order differential equation? Awesome. A sub 2 times x, y times y double prime plus a sub 1 times x times y prime plus a sub 0 times x times y is equal to, cool? All right. Now, the characteristic two properties of a linear ODE. The dependent variable y and all its derivatives y prime, y double prime, etc., all the way to that nth derivative of y, are of the first degree. That is, the power of each term involving y is 1. the coefficients A0, A1, all the way to A sub n of y prime, all the way to that nth derivative of y, depend at most on the independent variable x. Note, a nonlinear ordinary differential equation is one that is not beautiful, linear. All right, explain why the following are not linear ODEs. So this first term of part A, the e to the x is okay, right? Because it's a function of x, but and the second derivative is fine. But here you've got 4 minus y instead of something that does not depend on y. Remember, the coefficient cannot depend on y. Here, the coefficient does depend on y. All right, what about the second one? What do you think? Beautiful. Right here, we've got a nonlinear function of y. And so that's why it's not linear. Okay, solution of an ODE. Any function phi. So I know people say phi, theta, kappa, things like that. My instructors always said phi for this variable, so I say it phi. If you want to call it phi, that's cool. Any function phi defined on an interval I and possessing at least n derivatives that are continuous on I, which, when substituted into an nth order ordinary differential equation, reduces the equation to an identity, is said to be a solution of the equation on the interval. Note, the interval I can be called lots of stuff. The interval of definition, the interval of existence, the interval of validity, or the domain of the solution. And can be an open interval from A to B, say, a closed interval on A to B, an infinite interval, etc. Let's just call it A to infinity, non-inclusive. So looking back at the equation, capital F at x, y prime, all the way to that nth derivative of y equal to 0, we can rewrite it as capital F at x, phi at x for the y, phi prime at x for that y prime, and all the way down to the nth derivative of phi at x is equal to 0. All right, so for example 5, we're trucking right along here. Verify that the indicated function is an explicit solution of the given differential equation. Assume an appropriate interval of definition for each solution. All right, so our differential equation is dy dt plus 20y equals 24. And the solution we've been given is y equals 6/5 minus 6/5 times e raised to the negative 20t. All right, so first of all, we have a first order differential equation. So we might want to find the derivative of y with respect to t. So y is equal to 6/5 minus 6/5 times e to the negative 20t. So when I differentiate both sides with respect to t, we will have dy dt is equal to the derivative of 6/5 is 0, right? And then minus 6/5 times, what's the derivative of e to the negative 20t? Beautiful. Negative 20, the derivative of the exponent with respect to t, times the exponential as we saw it, e to the negative 20t. So cleaning it up, we have dy dt equals, this is going to be 24 e to the negative 20t. Cool so far? All right. So now let's look at verifying it. We've got the derivatives. So the left-hand side of the equation is dy dt plus 20y. And that, when we plug in what we know, is 24e to the negative 20t. So that one, remember, was our first derivative with respect to t. And then plus 20 times y. Y was given up here, right? So y is 6/5 minus 6/5 e times e to the negative 20t. And so that was our y. All right, so let's clean it up. 24e to the negative 20t plus 24, I'm distributing 20 throughout, minus 24e to the negative 20t. So this is going to just give me 24 because the exponential terms zero out. So the right-hand side is what? So easy it's hard, right? 24, which equals the left-hand side. So we have verified that y is an explicit solution of our differential equation. Okay, so secondly, we have a second order differential equation, and we have that means we have to find y prime and y double prime. So working on it, we started with y equals negative cosine at x times natural log at secant x plus tangent at x. So this will give us some review. So finding the derivative with respect to x of both sides. We will have dy dx, or y prime, is equal to negative sine at x, that's the derivative of cosine at x. And then utilizing the product rule, I'm going to write that second factor, natural log at secant x plus tangent x, just as it was. And then I'm going to add to that the first term, negative cosine at x, times the derivative of the second. So the derivative of the second's a little bit mean. Remember, you differentiate what's inside the log and then divide it by what was inside the log. So the derivative of secant at x is secant at x times tangent at x. Sorry about the dogs. And then the derivative of tangent at x is secant squared at x. And that's going to be over secant at x plus tangent at x. Cool? Okay, so we want to simplify that. I'm going to rewrite dy dx as y prime. So this will be sine at x times natural log of secant at x plus tangent at x minus cosine at x. Now, I'm going to change everything in terms of cosine at x. So secant at x is 1 over cosine at x. Tangent at x is sine over cosine at x. So we would have sine over cosine squared at x for the first term in the numerator, plus 1 over cosine squared at x over, so that's the numerator, over 1 over cosine at x plus sine over cosine at x. So we'll have y prime is sine at x times natural log at secant at x plus tangent at x. Now, if I go ahead and bring these terms together, I'll have minus cosine at x times 1 plus sine at x over cosine squared at x. That's the numerator, divided by 1 plus sine at x, this is looking good, over cosine at x, because they have like denominators. So y prime will be sine at x times natural log at secant at x plus tangent at x. Now, the 1 plus sine at x's are going to divide out when we invert and multiply. One of the cosine at x's in that first part will divide out, and the bottom one will completely divide out. Then we're going to have cosine x divided by cosine x, which is just 1, right? So we'll have minus 1. Pretty amazing, isn't it? All right. So now, let's go ahead and differentiate this result with respect to x on both sides to find the second derivative. So we'll get y double prime is equal to, so all of this again. So we'll have cosine at x times natural log at secant at x plus tangent at x plus sine at x times same derivative we had before, right? Same derivative we had before for the second part. So remember, we already did the derivative of natural log of secant at x plus tangent at x. And we simplified that to be what? Beautiful. 1 over cosine at x. That was before we brought the cosine at x in to divide it out to be 1. So y double prime is cosine at x times natural log at secant at x plus tangent at x plus sine at x over cosine at x is tangent at x. Groovy? Now that we've got the derivatives, we need to verify. So the left-hand side is, what is it? Y double prime plus y. Well, y double prime is cosine at x times natural log at secant at x plus tangent at x plus tangent at x, and then, so that was y double prime and then y is going to be what we started with, negative cosine at x. So negative, so we'll go plus negative cosine at x times natural log at secant at x plus tangent at x. And that was our y. And you'll see that the first and the third term will zero out. And so we're going to get tangent at x when that all is said and done. Let's look at the right-hand side. The right-hand side, lo and behold, is tangent at x, which equals the left-hand side. So we're done. It's verified. Cool? All right. Next up, definition 1.1.3, implicit solution of an ordinary differential equation. A relation capital G at x and y equal to 0 is said to be an implicit solution of an ordinary differential equation on an interval I, provided that there exists at least one function phi that satisfies the relation as well as the differential equation on the interval I. Here's another note. In upper division differential equations courses, you will have the opportunity to check out the conditions under which a relation, capital G at x and y equal to 0, defines a differential function phi. But for now, we assume that if the formal implementation of a method of solution leads to a relation G at x and y equals 0, then there exists at least one function phi that satisfies both the relation which was the capital G at x and y, G at x and phi at x equal to 0, and the differential equation on an interval I. We will go ahead and solve for y in terms of x and obtain one or more explicit solutions if the implicit solution is fairly simple. All right, so let's consider the relation x squared over 4 plus y squared over 9 equals 1. So what is that shape? Do you remember? Awesome, it's an ellipse. And so it's not a function because it doesn't pass the vertical line test or the horizontal line test, right? But the vertical line test is what defines a function. So this happens to be an implicit solution of the differential equation dy dx is equal to negative 9x over 4y on the open interval from negative 2 to 2. Looking at the original relation and differentiating implicitly and solving for dy dx, we have, so let's see what we've got. Basically just kind of reminding you how to implicitly differentiate. So let's write it out as x squared over 4 plus y squared over 9 is equal to 1. And then evaluating d dx of both sides, we will have two x over 4, the first term is explicit, plus 2y y prime. Actually, it said to use dy dx, so we'll use dy dx. 2y times dy dx over 9, so that one was implicit. And that's going to equal to 0, because the derivative of a constant is 0. And so we will have 2y over 9 times dy dx is equal to negative x over 2 when we simplify and then subtract to the other side. And that gives us dy dx isolated is going to be negative 9x over 4y. Cool? So, all right, let's scope it out. Let's solve the original relation for y. So here, remember we started with x squared over 4 plus y squared over 9 is 1. So then this would give us y squared over 9 is equal to 1 minus x squared over 4, which in turn would be y squared over 9 equals 4 minus x squared all over 4, just to pretty it up a little bit. And then multiplying both sides by 9 and taking the square root, we would have y is plus or minus the square root of 9/4 times 4 minus x squared, which of course would be y is plus or minus 3/2 times the square root of 4 minus x squared. So what is all that doing for us except a bunch of algebra and calculus? Now, let's check it out. What we're going to have is this kind of situation. So I'm going to make some pictures. Pictures are always nice. Positive 3. Okay, so let's check it out. So the first solution is implicit. And that was the one that was x squared over, I'm going to write it as 2 squared plus y squared over 3 squared is 1. That's an ellipse centered at the origin with the major axis, y having that being the major axis, right? So it's going to look like this. Cool. So that's our implicit solution. Now, one of our explicit solutions is y1, we'll call it, is equal to positive 3/2 times the square root of quantity 4 minus x squared. So what's that going to give us? The top half of the ellipse. So we'll have this situation here. And we could also represent that explicit solution using the negative, right? So we're basically picking constant factors. One was positive 1 for the y1. y2, if we picked negative 1 for our constant, we would get negative 3/2 times the square root of 4 minus x squared. And so we would have this situation here. Groovy? All right, so just sort of examining the differences between explicit solutions versus the implicit solution. And now let's check out families of solutions. When evaluating an antiderivative, or indefinite integral, it's really finding an indefinite integral. We use a single constant of integration, and we used to just call it C, right? For the most part. When we solve a first order differential equation, capital F at x, y, and y prime, we typically obtain a solution containing a single constant or parameter, C. A solution of capital F at x, y, and y prime. Oh, apologies, this should have been equal to 0 to make it an equation. Containing a constant C is a set of solutions in terms of capital G at x, y, and c, called a one parameter family of solutions. When solving an nth order differential equation, capital F at x, y, y prime, all the way down to that nth derivative at y equal to 0, we are looking for an n parameter family of solutions. Capital G at x, y, c1, c2, all the way to cn. equal to 0. And again, apologies, I should have had an equal to 0 up there. Oh, right. Thus, a single differential equation can have an infinite number of solutions corresponding to an unlimited number of choices. Isn't that amazing? For the parameter or parameters. A solution of a differential equation which is free of parameters, which you've probably encountered, is called a particular solution. So, example 7, we want to verify that the family of functions is a solution of the given differential equation. We're assuming an appropriate interval of definition for each solution. So, here we go. We've got a third order differential equation here on the left, and then the solution on the right is y. So, what do we need to find? Beautiful. We need to find the third derivative, which means we need to find the first and the second too. All right, so y prime is going to be, using that power rule, negative c sub 1 times x to the negative 2 plus c sub 2, and then plus c sub 3 times the derivative of x times natural log at x with respect to x is going to be 1 times natural log at x plus x times 1 over x. I'll simplify that in the next step. And then the next one is 8x. So y prime will be negative c1 x to the negative 2 plus c2 plus c3 times natural log at x plus c3 times 1. Just distributing the c3 throughout and simplifying, and then plus 8x. All right, y double prime will be 2c1 x to the negative 3. The c2 term will zero out, and then we will have plus c3 times 1 over x. The c3 zeroes out, plus 8. So in place of that 1 over x, let's write it as x to the negative 1, which makes it easier to find that third derivative. So we'll have negative 6c1 x to the negative 4 minus c3 x to the negative 2, and the 8 will zero out. Cool, cool? All right. Now, what do we need to do? We need to go ahead and plug it in to the differential equation and see what we get. So the left-hand side of our differential equation is x cubed, the third derivative. So we're going to put in negative 6c1 x to the negative 4 minus c3 x to the negative 2. So my third derivative is going in here. All right, plus 2x squared times our second derivative. Our second derivative is 2c1 x to the negative 3 plus c3 x to the negative 1 plus 8. We found that one here, and we're plugging it into that part. And then minus x times that first derivative, which was negative c1 x to the negative 2 plus C2 plus C3 ln x plus C3 plus 8x and then, sorry, it's, maybe I can pull it over. Gotta love technology, right? All right, perfect. And we still have a little bit left. That last little bit was plus y. And yeah, I don't think it's going to end up fitting. So we'll have to do it over here. I'll just say plus y, and y was equal to that original c1x to the negative 1 plus c2x plus c3x times natural log at x, and then plus 4x squared. Now this all is going to equal to negative 6 c1 x to the negative 1. I'm just going to distribute everything through. So x cubed times x to the negative 4 is x to the negative 1. And then we'll have minus c3 x to the 1. And then plus 4 c1 x to the negative 1. So at first I distributed the x cubed. Now I'm doing the 2x squared. And we will have plus 2c3 x to the 1 plus 16x squared. And then distributing the x throughout, we shall have plus c1 x to the negative 1 minus c2 times x minus c3 times x natural log at x minus c3x minus 8x squared, and then plus c1x to the negative 1 plus c2x plus c3x times natural log at x plus 4x squared. That will equal to, so a lot of stuff is going to zero out. So we have negative 6 c1 x to the negative 1 plus 4 c1 x to the negative 1 gives us negative 2 c1 x to the negative 1. Then we have a positive here. Now it's negative 1. So I'm looking at this one, this one, this one. And then we have another one here, which is 0. c1 x to the negative 1s are just 0. And then looking at the c3x's. So now we've got negative 1 here, positive 2 of them here, so that'd be positive 1. And then minus 1 will zero it out. So plus 0, c3x's. And now looking at this x squared terms, we have 16x squared minus 8x squared is 8x squared plus 4x squared is 12x squared. And then c2x, we have a negative, we have a positive, that zeroes that one out. And what else do we have? We have a negative c3x times natural log of x and a positive, which zeroes that one out. And then that, of course, is just equal to 12x squared. The right-hand side is, come back up, lo and behold, 12x squared, which equals the left-hand side. Check. Phew! All right, perfect. Now we've got a piecewise defined function. When x is less than 0, y is negative x squared. When x is greater than or equal to 0, y is positive x squared. This is a solution of the differential equation xy prime minus 2y is 0 on the real line, negative infinity to infinity. So here we go. If we take a look at the derivative, do you see that y prime is equal to negative 2x for x less than 0. Y prime is equal to positive 2x for x greater than or equal to 0. So actually, we could just write this as another piecewise function, right? Groovy? So let's check it out. If we take a look at this on using both of those slopes, right? So let's do y prime 1 equal to negative 2x. So we'll have the left-hand side is x times that first y prime, which is negative 2x, minus 2 times y, well, the y that goes with that one is negative x squared, is equal to 0. Whoops, that's the right-hand side, my bad. This is just equal to 0. The right-hand side is 0, which is equal to that left-hand side. Check. So let's take a look for y prime at 2 equal to positive 2x. The left-hand side for that one is what? Beautiful. We'll have x times positive 2x minus 2 times positive x squared. That's going to equal to 0. And our right-hand side of that differential equation is 0, which is equal to the left-hand side. Check. We got it. Cool, cool? Isn't differential equations fun? All right. So example 9. Find the values of m so that the function y equals e to the mx is a solution of the differential equation. All right, well, we have a second order differential equation. So we need those derivatives. So y prime is going to be, beautiful, me raised to the mx. Y double prime will be m times m, which is m squared, e to the mx. Because remember, we're differentiating with respect to x. So 2 times y double prime, we'd have m squared e to the mx. Plus 7 times y prime, which was me to the mx, minus 4 times y. Y originally was just e to the mx equal to 0. So I got these from the work over here. And double prime. All right, so now, all right, what do we have? If we factor out an e raised to the m times x, we're going to be left, because that's what's in common with all of them, we're going to be left with 2 times m squared plus 7 times m minus 4, and all of that would equal to 0. So what does that mean? E to the mx is 0, or 2m squared plus 7m minus 4 is 0. The first one is extraneous. There's no way that that exponential can have a 0 result, so we'll cross that out. So here, factoring, we'll have 2m, if we go plus 4 on the second factor, and if we go, that will give us an 8m, and if we just do minus 1 on the first factor, you'd have a positive 7m, and we still get everything we need. Perfect. So that means that 2m minus 1 is 0, or m plus 4 is 0. So m is 1/2, or m is negative 4. And we're all done. All right, beautiful. Well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that like button and subscribe. Bye.